Welcome to the Deep Dive. Today we're tackling what looks like maybe one of the most obscure things in math, a single sequence from the online encyclopedia of integer sequences, A000377.
That's right. And it starts off simply enough. 1, 1, 1, 1, 2, 1, 2, 1, 1, 2, 1, 0, 2, 2. Looks a bit random, maybe.
Yeah, just a string of numbers.
Yeah.
But here's the hook you told me. Something about the average.
Exactly. If you average these numbers out as the sequence goes on, the mean value isn't random at all. It's perfectly dictated by the constant pi.
Pi. That seems wild. How could a sequence of, well, just plain integers have its average tied to pi divided by the square root of 6, which is what, about 1.2825?
Okay, 0.2825 and so on.
Okay, so what's the engine behind this? What defines E000377 to give this profound structure?
Well, the structure comes from how it's generated. It's defined by sophisticated mathematical objects called theta functions, specifically Ramanujan theta functions.
Ramanujan, okay, big name. But before we get lost in the, the Greek letters and the functions like FQ, GQ, what does using these theta functions actually guarantee for the sequence?
It guarantees a high degree of order. It's not random. Historically, this type of definition connects back to people like P.A. McMahon and Nathan J. Fine. They use these kinds of identities to study partitions, number partitions.
Okay, so there's history there, partitions.
And what's really fascinating is that there's a completely equivalent way to define it using different functions, the Dedekind eta functions. We call this an eta-quotient definition.
An eta-quotient. So two different complex function definitions give the exact same sequence.
Precisely. The theta and eta definitions are like its mathematical DNA. And this specific eta quotient isn't just some random combination either. It's actually item number 42 in a well-known table published by Martin back in 1996.
42. So this is plugged right into, current research on multiplicative functions.
Absolutely. And this structure, this eta-quotient identity, forces the sequence to have a really neat property called multiplicativity.
Multiplicativity, right.
Yeah.
That means you can figure out any term, say an, just by knowing how it behaves for prime powers, like ap to the power of e, right?
Exactly. You break down n into its prime factors, figure out the a value for each prime power part, and then just multiply them together.
Okay, but hang on. The notes here say something, well, frankly, weird. It says a2n, a3n also equals an. So the sequence just ignores multiplication by 2 or 3. That feels very counterintuitive for something generated by these complex functions.
It is highly unusual, yes, especially for sequences tied to modular forms, which this one is. But the real, I'd say, elegance shows up when you look at the prime behavior based on modulo 24 arithmetic.
Ah, modulo 24. That was to explain some of those zeros we saw earlier in the sequence. 1, 1, 1, 1, 1, 2, 1, 2. Then later is 0. How does that work?
Right. So if you take a prime number p and look at its remainder when divided by 24, if p is congruent to 1, 5, 7, or 11 modulo 24, the rule is simple. ap to the e is just e plus 1.
Okay, e plus 1. Simple enough.
If the prime p is congruent to 13, 17, 19, or 23 modulo 24, the sort of other half, then the terms ap to the e actually alternate. 1, 0, 1, 0, and so on.
Ah, so ap squared would be 0 if p is in that second group, and ap cubed would be 1 again.
Exactly. And that's why the sequence hits 0 quite often. It's baked into the rules for these primes.
And this strange but very precise behavior based on modulo 24 that must be enforced by this deeper connection to modular forms you mentioned.
That's the ultimate guarantee, yes. The generating function itself obeys a specific transformation rule related to modular forms. It's complex, involves roots of 24 and I, the imaginary unit, but it dictates the structure.
So it all ties together. The fancy functions, the multiplicativity, the weird rules for 2 and 3, the modulo 24 behavior, the zeros.
And it brings us right back to that payoff we started with. The asymptotic mean, the fact that the average value of these integers settles down to exactly pi divided by the square root of 6. It's a beautiful sign that this sequence isn't arbitrary. It's governed by, well, fundamental constants of mathematics.
Amazing. Before we wrap up with a final thought on A000377, let's take a very brief moment for our sponsor. We'd like to thank embersilk.com for sponsoring this deep dive. Embersilk is the answer for all your AI education and integration needs. Find out more at embersilk.com. So recapping this sequence, A000377, it starts with these complex definitions using theta and eta functions, things from deep number theory.
Right, from Ramanujan, Dedekind.
But they unpack into these surprisingly elegant, almost simple integer properties. Perfect multiplicativity, that strange A2 and AN rule, and this average value tied directly to pi.
Indeed. It shows how these abstract functions can encode very concrete, structured information about integers. And, for listeners who want to dig even deeper, there's more. This sequence, A000377, can also be generated through other fundamental operations in number theory. It's the Möbius transform of one sequence with period 24, and it's also the Euler transform of another sequence with period 24.
Wow. So like multiple different mathematical lenses are all focusing on this exact same sequence of integers.
Precisely. It just demonstrates how deeply interconnected these concepts are.
Truly mind-opening stuff. Thank you so much for guiding us through this fascinating corner of the mathematical universe.
My pleasure.
And thank you, our listener, for joining us on the Deep Dive. If you enjoyed getting this insight, please do subscribe, and if you can, leave us a 5-star review. It genuinely helps us keep bringing you these deep dives. Thanks for listening.